all, and welcome to our last big topic in chapter 11. And we're going to spend a couple days on this because it is a complex idea, but one that has a lot of problems on the AP, first of all, and a lot of importance in larger mathematics. So get yourself ready for notes. This is going to be a longer video, and then you're going to have 2 days to practice, as you can see here. So let's get started. Now, we're going to talk about specific subset of series. These ones, unlike geometric or something like that, are named after the people who published about them. So we have Maclaurin and Taylor series. They're pretty much the same. There's a couple slight differences. And the idea with both Taylor and Maclaurin series is this is the principal idea. A polynomial can approximate any function with a high enough degree. Now, what this means here is I have the graph sine of x. So if we think about sine of x and the origin point, 0, 0, that's, by the way, what makes it a Maclaurin series versus Taylor is just centered at 0 versus at another random number. If I have this sine curve, if I just consider the first derivative, that creates a tangent line, which is a very good approximation directly here and becomes a very terrible approximation very quickly. However, if I create, in this case, sine the second derivative is going to be sine again, so that's 0. So if we just take the first derivative, the second, which is 0, and the third, we get a cubic function, and we can see that the cubic function here is this orange function. So we're now at a third degree function. And what we actually are seeing is, okay, it's actually a pretty good approximation now all the way to here. So a little bit better than our linear. We then have a 5th degree polynomial. And we can see that that's getting pretty good. It's a good approximation all the way out to about here. The next one would be a 7th degree polynomial. And you can see as the degree goes up and up, we get an increasingly better approximation. And hopefully you can imagine that if we went to an infinite degree, and having an infinite series is just fine, this polynomial, so coefficient plus power something x, x squared, x to the third, x to the fourth, and so on for any function, if we go to infinity, it will be the same as this function all the way across. And that's the idea of a Taylor series, is writing out this polynomial. So then the question becomes, all right, if this is the polynomial, here we're centered at 0, if you remember the idea of centered from last week's lesson. Centered at 0 just makes the notation a little bit easier, but you could absolutely have it centered at a different point, whereas instead of x, you have x minus a, just like we saw in last week's lessons, but adding all those in just takes up a lot of space. Then, okay, well, if I plug in 0, which is where it's centered, or a, I understand that f of 0, 0, 0, 0, these all cancel out. The first coefficient is just the function at 0. If I take the derivative of the function, plug that in, plug in 0. Yeah, it's just a polynomial, power rule, all the way down. Plug in 0 again. The coefficient of the second term is f prime. Now, when I take the derivative again, this cancels out. Power rule, x brings down to 2, brings down to 3. We get this polynomial. So when we plug in 0, we get that the coefficient of the x squared term times 2 is equal to f prime of 2. So the coefficient 2 has a coefficient 2 at x squared is the second derivative at the 0 over 2, just dividing that over. If you want to continue this work out, what you'll realize is that the nth coefficient, so whatever this is a nice formula, is the nth derivative at 0 over n factorial. Because it's factorial because every time we take the power rule, this comes down, so this would become 3 times 2, which is 3 factorial. This is 4 times 3 times 2. The next term would be 5 times 4 times 3 times 2, and so on. So that's what's creating a factorial. So what this actually gives us is a nice formula for this series here. So what this tells us is that the function of x is equal to this long polynomial. So C0, which is f of 0, plus f prime x plus the second derivative over 2 plus, all the way out, the nth term would be x to the n, and f of n, the nth derivative at 0 over n factorial. Keep going out. What we'll usually write this as is a series. So the series, so this function is exactly equal to the infinite series as starting from n equals 0 of f to the n at 0 over n factorial x to the n. Now this is Maclaurin because it's centered at 0. So centered at 0 means that we have this 0 here and x by itself. This is our Maclaurin series. Now you'll see a Taylor series centered here. Taylor series states nearly exactly the same thing, but what's different is that it says that f of x, it's just the centered point is different. So it's equal to the infinite series from n equals 0, f of n, the nth factorial at the center, which is a, over n factorial, and then x minus a to the n. So the only difference between Maclaurin here is centered at 0. Taylor, you can center it at any point. And these power series that are being formed, because this is a power series, it's times x to the a power, can be really useful. They're going to be really helpful tools to integrate and differentiate with, and we'll see some examples of that later on. Right now we're just going to focus on writing them. And they're also extremely helpful in several other areas of mathematics, like I said. So, but for this next 2 lessons, we're just going to focus on writing these Maclaurin series. So here, we started with the example sign, so let's actually write this out. Write the Maclaurin series of f of x equals sine of x. So what I generally will do with these problems is, since we're looking for f, the nth derivative at 0, because it's Maclaurin, over n factorial, x to the n, I'm going to start by just making a table, and you'll see the book does this as well, where we think about what n is, and I'm just going to write out the first couple terms, the nth derivative, and then the nth derivative at 0. So here, 1 is always just the function itself. So in this case, sine of x, 1 cosine of x is the first derivative. The derivative of that, negative sine of x, negative cosine of x, positive sine of x. And hopefully by now you start to see a pattern that as this keeps going on, we're just going to keep rotating between these just like so. So when I plug in 0, we get 0, 1, 0, negative 1, 0, and if you wanted to continue the pattern, you would then have positive 1 again, negative 1, and so on. So in our polynomial, if we wrote it all the way out, we are going to have the first term, right? That's this one here, 0, plus 1 over 1 factorial, x, plus 0 over 2 factorial, x squared, plus negative 1 over 3 factorial, x to the third. Because remember, these two are just matching. So when we write our term, we divide by n factorial times x to the n. plus 0 over 4 factorial x to the 4th, and so on. Now for sine, you'll notice we have 0, 0 over 2 factorial is 0, 0 over 4 factorial. So what we end up with is 1 over 1x plus negative 1 over 3 factorial x to the 3rd, plus, if you can imagine going farther, 1 over 5 factorial x to the 5th, plus negative 1 over 7 factorial x to the 7th, because it's going to be a pattern it's going to keep repeating. So what you'll notice here is that sine just has only the odd powers and the odd denominators, plus you have an alternating part. It's positive, negative, positive, negative. So we know that it's odd and alternating. So when I write out my series, I say sine of x is equal to series from n equals 0 to infinity of alternating, which is negative 1. And since we start at 0, we start with a positive. So this just becomes the question. Want to start with a positive? We can just say n in this case. If we want to start with a negative, we would say n plus 1. And then the way that we write odd numbers for our factorial is we say 2n plus 1. Because 2n are our even numbers, and then 2n plus 1 are our odds, and those match up with the powers. So 2 to the n plus 1. And this would be the Maclaurin series for sine. Now, there's a couple Maclaurin series that I just recommend you have memorized. Sine is this one here. I'm going to erase some space over here. Cosine is also one. And then the third one that I recommend that you just memorize is e to the x, which we're going to do next. So if cosine is the other one, as you can maybe imagine, if sine is all the even powers, cosine is going to be all the odd powers. Because basically what cosine is doing is just starting you from there, saying that this is 0, 1, 2, 3. So you've got f of x, the second derivative, and so on. So n equals 0 to infinity of negative 1, since we're still starting at positive, that's fine, over 2n factorial x to the 2n. So cosine are all the even terms, alternating, and cosine are all the even terms, sine are all the odd terms. Now, write the Maclaurin series for f of x equals e to the x and find its radius and interval of convergence. So this is one that's really common to memorize, and the main reason for that is the nth derivative of x for e to the x is just e to the x. It's the same thing, right? So we always know what our f to the nth derivative of 0 is equal to e to the 0, which is 1. And this is why it's one of those ones that's just really commonly memorized. So when we plug that in to our formula, e to the x is equal to the series from n equals 0 to infinity. And if we just plug it in, we end up with the nth derivative at 0 over n factorial x to the n. We can substitute here, since that's always going to be 1. And so e to the x is equal to the series 1 over n factorial x to the n. So that's sort of like, if you think about it as the most basic Maclaurin series. So if you just have 1 here, using our formula, it's equal to e to the x. Really common one. You'll also sometimes see it as x to the n over n factorial. That's just taking that multiplication one step further. Now, to find its interval and radius of convergence, so I'm just going to draw little dotted lines through here. So we've got those separated. I'm going to always use the ratio test for these problems because you have a factorial down here. And remember, we want to use the ratio test whenever we see a factorial. So in this case, I'll take the limit as n approaches infinity of x to the n plus 1 over n plus 1 factorial divided by x to the n over n factorial. And I want to set that less than 1. Simplify that. We end up with the limit of the absolute value of x over n plus 1. Whoop. It's not less than 0, it's less than 1. Just through canceling out with that term there. Now, what you'll notice here is that as n approaches infinity, we get x over infinity. X stays the same, but if you divide any number by infinity, you do get 0. So this limit equals 0, which is less than 1. So what that means, x doesn't actually matter. That means that this converges for all real numbers. So x can be anything, and because that limit's always equal to 0, which is less than 1, it converges for all real numbers. So no matter what you plug in here, that series will still equal e to the x. Now let's practice with the Taylor series, because Taylor series, remember, is just centered at something other than 0. That's the only difference. So write the Taylor series for f of x is equal to x to the negative 2 centered at 1. This is why you don't want to center it at 0, because if we plugged in 0 to this function, it's at an asymptote. So I'm going to do the same thing that we saw before. And I'm going to make myself a table just for the first couple. 0, 1, 2, 3, 4. The nth derivatives, x. And then the nth derivatives at the center, which in this case is 1. So our first one is just our formula, x to the negative 2, negative 2, x to the negative 3, negative 2 times negative 3, x to the negative 4. And as you might see here, we're creating a factorial again. So then this becomes, so then we have 6 here as our lovely positive term. So if I plug in 1, 1, negative 2, positive 6, negative 2, negative 3, negative 4, x to the negative 5. So then this becomes negative 24. We could continue following the pattern. Hopefully you also notice it's alternating here. So then this is 3 factorial, 4 factorial. So this would be positive 5 factorial. And if we then think about what our general term is here, it's alternating, which we start with this, as a power. Since it started positive, we'll do n. And then you have a factorial. And you'll notice here the factorial is 1 bigger. So like 1, here's 2 factorial, 2, this 3 factorial, 3 goes to 4 factorial. So we write this as n plus 1 factorial is equal to the nth derivative at 1. So that's our formula right here for our numerator. So when I plug this in, we can say x to the negative 2 is equal to the series from n equals 0 to infinity of nth derivative at a. So negative 1 to the n times n plus 1 factorial all over n factorial from the denominator here times x minus 1 to the n. Now, of course, you'll hopefully notice that you can simplify that, and that's equal to the series. The factorials simplify. You still have the alternating section, negative 1 to the n times n plus 1, x minus 1 to the n. And you could even go a little bit farther. You notice that these are both powers. So you can multiply those together. And I think in its most simplest form, I would express this as the series as n equals 0 to infinity of n plus 1 times 1 minus x, using that negative to change the power over to the power of n. So, like I said, this table situation is really helpful until you notice what the actual pattern is going to be, and then you want to use the different tools that you have to simplify as you go. If you have questions on any of these problems, please nominate them in the forum or reach out on Zoom, email, or in the Google comments. Talk to you later.